March 17, 1943, Recklin Experimental Airfield, Germany. Hans Verlicher's hand quivered as he made the first entry in his logbook, noting an incident that would append Luftwaffe assumptions about their opponent. It seemed impossible that the Americans could have produced thousands of such machines. No nation, the thinking went, could turn out that level of complexity and quantity while fighting a global conflict. From the cockpit of the captured Boeing B-17 Flying Fortress marked DLX-K by German crews, Lurcher examined an instrument panel that contradicted 3 years of German intelligence. The most advanced versions of this bomber carried up to 13 defensive gun stations. The B-17F before him mounted 9 heavy machine guns, each capable of roughly 750 rounds per minute, forming overlapping fields of fire that made the aircraft something new in aerial combat. In German hands, the seized Fortress, nicknamed Wolfhound, was the first intact American heavy bomber available for test flights. What Lurcher and the other evaluation pilots learned in the months after would deal a greater blow to German confidence than any single battlefield loss. The concentration of firepower in one bomber, when multiplied across the hundreds flying tight defensive formations, created an aerial threat German fighter tactics had not encountered and German industry could not easily match. The conversion of an enemy weapon into an intelligence treasure began 3 months earlier. On December 12, 1942, Lieutenant Paul Flickinger, piloting B-17F serial for 124585 with the callsign Pub, was on a bombing run against the Rouen-Sauterville rail yards in occupied France. His plane, belonging to the 361st Bombardment Squadron of the 303rd Bombardment Group based at RAF Molesworth in Huntingdonshire, England, carried the informal name, Wolfhound, painted on the nose by ground personnel. The 303rd, nicknamed Hell's Angels, had seen its first combat only weeks earlier and still lacked deep combat experience. That December morning, the group sent 20 B-17s toward Luftwaffe service facilities about 60 miles east of Paris. The mission began normally, but German fighters from several units had other intentions. Messerschmitt Bf-109s and Focke-Wulf Fw-190s attacked the American formation relentlessly, pressing hard because breaking the tight defensive boxers offered the best chance of success. Bullets and cannon rounds ripped through Wolfhound's fuselage and wings. One engine quit and windmilled uselessly. Another lost power with smoke trailing from damaged cylinders. As his crippled bomber fell behind the protective formation, Flickinger faced an impossible decision. The rest of the B-17s pressed on toward England, unable to slow without inviting the German fighters. Trying to reach England alone, across the Channel, would likely mean destruction for a plane that could no longer keep station. Diverting toward neutral Switzerland or Sweden meant hundreds of miles over hostile territory with failing engines and enemy aircraft in pursuit. The only realistic hope for his crew was an immediate forced landing on territory controlled by the enemy. Picking through gaps in cloud and engine smoke, Flickinger found what looked like a suitable field near Melun, France, roughly 60 miles southeast of Paris, with remarkable skill given the damage. He put the massive bomber down in a wheels-up landing in a hayfield. The B-17 slid across grass and mud, its ball turrets scraping the ground, carving a long furrow before coming to rest. The 10-man crew climbed out with hands raised, expecting to be taken prisoner, unaware of how valuable their intact aircraft would prove to German intelligence. Within hours, Luftwaffe ground crews and Wehrmacht soldiers swarmed over the captured fortress. Engineers photographed every system and structural detail before souvenir hunters or saboteurs could damage it. Most Allied wrecks came to rest broken across fields and forests, their secrets buried in twisted metal. Wolfhound, however, sat nearly whole in a French meadow, a complete example of American heavy bomber design ready for exploitation. Recovery specialists immediately realized the importance of their find. This was not scrap, but the first flyable B-17 the Luftwaffe had seized. The opportunity to study American design, construction techniques, defensive armament, and operational systems was unparalleled. Technicians moved quickly to ferry the damaged but repairable bomber to Leeuwarden Airfield in the Netherlands, a major Luftwaffe base built from a pre-war Dutch civil airport. Transport required careful planning to avoid further harm to the prize. 2 days after capture, on December 14, 1942, German mechanics finished temporary repairs to the battle damage, topped off the tanks with German aviation fuel, and painted German markings over the American insignia, black crosses on the wings and fuselage and a swastika on the tail, the colors and markings announcing the bomber's new ownership. 2 Messerschmitt Bf-110 heavy fighters escorted the aircraft while a selected German crew prepared to fly it to Recklin, the Luftwaffe's principal testing and evaluation center, about 50 miles north of Berlin in Mech. The flight plan was circulated to Luftwaffe fighter bases and flak batteries along the route with strict orders not to engage the captured fortress. Yet despite these measures and the clear markings, some German units still fired on their own prize. causing minor additional damage before recognition signals stopped the attacks. An episode that revealed both the eagerness to destroy American bombers on sight and the challenges of coordinating a sprawling command structure, strained by multi-front warfare. When Wolfhound arrived at Recklin, it entered a place devoted entirely to reverse engineering enemy aircraft, the central evaluation facility, equivalent to the U.S. Wright Field or Britain's Royal Aircraft Establishment at Farnborough. Every captured Allied plane that could be made airworthy found its way here, where German engineers dissected foreign technology to find weaknesses, copy innovations, or devise counters. Hundreds of technicians, engineers, test pilots, and support staff worked solely to learn how enemy aircraft functioned and how best to defeat them. For 3 months after mid-December 1942, Wolfhound remained grounded while specialists conducted exhaustive inspections. Panels were removed to examine structural details, and technicians admired the stressed skin construction that gave the B-17 its famed resilience. They measured skin thickness, analyzed alloys, tested rivet patterns, and joining methods. Every system was recorded in detail. The miles of electrical wiring revealed American approaches to systems integration. Hydraulic controls showed advanced valve designs and pressure regulation. The oxygen distribution system pointed to high-altitude capability. The intercom system allowed clear crew communication despite engine noise. The fuel management system let crews shift fuel between tanks to maintain balance. And the engine synchronization gear reduced pilot workload while optimizing performance. Each part was photographed, sketched into technical drawings, measured precisely, and compared with German equivalents. Luftwaffe aeronautical engineers were struck by the American manufacturing philosophy evident in the B-17. Bomber demonstrated mass production methods at a scale German industry had neither achieved nor seriously attempted. Standardized components that fit together without custom fitting, interchangeable parts for quick replacement in the field, and simplified assembly sequences that allowed semi-skilled labor to build complex airframes using jigs, templates, and fixtures. In contrast, German practice often required skilled craftsmen to hand-fit intricate parts through labor-intensive processes. The implications for German planners were profound. If one captured bomber showed such manufacturing sophistication, suggesting an industrial system optimized for volume production, how many could American industry produce in a month or a year? German analysts' calculations produced figures that seemed implausible, yet proved conservative. On March 17, 1943, Wolfhound finally flew under Luftwaffe control for the first time. Flugführer, an experienced test pilot, chosen for his judgment and skill, made the maiden German flight from Recklin. The bomber handled smoothly for its size, responding to controls with surprising docility. German test pilots confirmed what intercepted American reports and prisoner interrogations had hinted. The B-17's flight characteristics were excellent. The Fortress flew with notable stability for an aircraft with an empty weight around 15 tons and a maximum loaded weight near 30 tons. Control responses felt predictable and balanced across the flight envelope. Even with 1 or 2 engines shut down during deliberate tests, the bomber remained controllable, which explained why so many badly damaged B-17s managed to limp back to England, while similar damage would have been fatal to many German types. Over the following weeks, in spring 1943, several German pilots flew Wolfhound in a variety of test profiles to explore its performance. High-altitude trials showed the bomber could cruise comfortably above 25,000 feet. Where German flak became less effective due to reduced shell velocity and longer time of flight. Engine synchronization tests exposed sophisticated constant-speed propellers and automatic governors that eased pilot workload, while keeping engines near optimal power. Formation flying exercises demonstrated the aircraft's stability in close proximity to wingman, explaining how Americans maintained tight defensive boxes that Luftwaffe fighters found so hazardous to penetrate without entering concentrated fields of defensive fire. The B-17's handling made it ideal for formation bombing, where dozens of aircraft had to hold precise geometric patterns while under attack. But the trials that most influenced German fighter tactics centered on the defensive armament. Understanding the B-17's weapons layout became the Luftwaffe's top tactical priority in the West. German fighter pilots needed to know the Fortress's blind spots, the approach angles that offered the best chance of survival, the ranges at which German cannons could be brought to bear without entering the deadly envelope of American guns, and the tactics honed by American crews through painful experience. The numbers alarmed German planners. The B-17F carried 9 Browning M2.50 caliber machine guns positioned to provide overlapping fire across nearly every attacking vector. Later versions, particularly the B-17G, introduced in mid to late 1943, would increase that count to 13 with the addition of a chin turret and improved nose armament. Even 9 heavy machine guns was defensive firepower well beyond that fitted to German bombers. German bombers typically relied on fewer, often improvised or cramped defensive stations with limited traverse. The Heinkel He 111, A standard medium bomber usually carried 6 or 7 machine guns of mixed calibers, many of them 7.92 rifle caliber, weapons with limited effect. Against fighters and the Junkers route, 88 might field only 4 or 5 defensive positions. By contrast, the American B17F came standard with 9 heavy machine guns, a defensive suite that reshaped how the Luftwaffe viewed daylight bombing raids. Every bullet discharged was a .50 caliber round, capable of piercing armor plate, wrecking engines, shattering canopies, and killing aircrew at distances beyond 600 yards. The .50 BMG cartridge. These guns used delivered roughly 3 times the kinetic energy of German 7.92mm rounds and comparable energy to German 13mm heavy machine guns. Hans Verlier, who would become the Luftwaffe's most seasoned test pilot for captured Allied types, flew Wolfhound repeatedly through the spring and summer of 1943. His memoir published after the war, Luftwaffe, Test Pilot, Flying Captured Allied Aircraft of World War II, later gave detailed recollections of his time with the Fortress and many other captured machines. Lear treated captured airplanes as technical problems to be solved, not as ideological trophies. And that professional detachment made him indispensable to the evaluation program. His university engineering studies, combined with years of glider and powered aircraft experience, gave him the analytical eye and flying skill needed for the risky work of testing unfamiliar enemy types. Over the course of the war, he flew more than 125 different aircraft models without suffering a single major crash or serious damage incident, a safety record that reflected both meticulous technique and sound judgment. When Lear climbed into Wolfhound's cockpit for the first time, there were no manuals, no training syllabi, no checklists, and no experienced instructor to walk him through systems. He learned by looking and probing, forming hypotheses about controls and systems, and validating those assumptions aloft where errors were less likely to be instantly fatal. The instrument panel's layout differed sharply from German practice in organization and underlying philosophy. American designers tended to centralize gauges in standardized locations that were consistent across types. Easing transitions between aircraft, circuit breakers replaced many fuses in the electrical system, offering resettable protection that simplified troubleshooting. Hydraulic pressure gauges used imperial units calibrated in pounds per square inch rather than metric. The throttle quadrant's logic was reversed compared with German types. Moving the levers forward increased power rather than reduced it. Perhaps most striking to Lear was the bomber's sheer toughness and tolerance for damage. The B-17 could sustain punishment that would have finished comparable German airplanes and still remain airborne and controllable. Its structural resilience derived from heavy-gauge aluminum frames and stress skin construction that distributed loads across the airframe. Multiple redundancies meant that single failures seldom spelled catastrophe for the mission. Self-sealing fuel tanks reduced the risk of fire from smaller caliber hits, a feature the Germans understood technically but had not implemented so widely, and armor plating protected vital stations and systems, with special attention to the pilots, engines, and fuel lines. Lear and other test pilots at Recklin carried out many firing trials to analyze the B-17's defensive package from the attacker's point of view. The prospective German fighter pilots would need most Messerschmitt Bf-109 and Focke-Wulf Fw-190 pilots climbed into their fighters to make simulated attack runs on Wolfhound while it flew straight and level or executed evasive maneuvers. Ground observers photographed passes and logged approach angles, ranges, closure speeds, and exposure durations. Combat cameramen filmed from chase planes to produce training films for fighter units across Germany and occupied Europe. The exercises exposed uncomfortable facts that contradicted earlier assumptions about bomber vulnerability. The traditional tactic of attacking directly from which had worked against older, lightly defended bombers, exposed the fighter to concentrated defensive fire on the B-17. The tail gunner, seated in a powered turret with excellent visibility through clear plexiglass, commanded a wide and unobstructed field of fire with no blind sectors within about 30 of the rear axis. The dorsal turret, a powered Sperry mount with .50 caliber guns, could swing aft and add its fire to the tail gunner's barrage, effectively doubling the heavy gun fire directed at a rear approach. Waist gunners manning open windows along the fuselage could also engage attackers coming from behind, below, or slightly to the sides. A fighter closing from 6 o'clock directly aft, therefore faced at least 4 heavy guns, focused along a predictable interception corridor. The tail gunner alone could bring 2 weapons to bear, and at effective ranges his fire could quickly shred the thin skin of single-engine fighters. With relative speeds between attacker and target typically in the 150 to 200 miles per hour range, a German pilot might have only 3 to 5 seconds to fire before having to break off. And during that brief window the bomber's gunners could pour hundreds of rounds into the approach corridor, creating a cone of fire the fighter had to penetrate. Luftwaffe, after-action reports documented many cases of fighters damaged or destroyed making tail attacks. and survivors described the experience as flying into a storm of tracers, a phrase that captured the visual and psychological intensity of facing massed defensive fire. At common engagement distances of 400 to 800 yards, roughly 1 in 4 or 5 rounds was a tracer, producing visible streams of fire that made attacking aircraft seem surrounded by luminous streaks. Those tracers, while intended to help gunners observe fall of shot, also produced a powerful deterrent effect. German pilots often encountered walls of converging tracer fire and instinctively broke off before reaching the optimal firing window, reducing their effectiveness even when hit probabilities remained modest because of the difficulty of deflection shooting at high closing speeds. Attacks from underneath posed different but no better prospects. The Sperry ball turret on the bomber's belly covered the lower hemisphere with no blind spots, placing a gunner in a rotating sphere equipped with .50 caliber guns and a mechanical computing site that helped calculate lead for fast targets. Crowded into cramped quarters with knees drawn up and oxygen mask pressed to the sight, the ball turret gunner could traverse 360 of azimuth and nearly 90 of elevation from horizontal to almost straight down. The position was physically demanding and too small for a parachute, yet its coverage was unmatched. No approach from below escaped its field of fire. German pilots learned painfully that running in underneath a B-17 formation exposed them to concentrated, mechanically aimed salvos from multiple ball turrets. Beam attacks encountered the waist gunners, who stood in open windows at extreme altitude, enduring near-zero temperatures, hurricane-force slipstream, and relentless engine noise that made coordination difficult. The B-17F's staggered waist positions prevented gunners from getting in each other's way while maximizing coverage. One gunner stood slightly forward on the port side, the other slightly aft on the starboard, each manning a .50 caliber weapon on a flexible ring that allowed wide traverse in elevation. Beam approaches, therefore, often meant flying through crossfire from both waist guns plus the dorsal turret, which could rotate to bring guns to bear above the horizontal plane. Those interlocking arcs of fire created zones where multiple weapons engaged a single attacker at once, concentrating fire and markedly increasing hit probability. The overlapping defensive pattern forced German fighters to adopt fast slashing passes rather than sustained guns and runs, reducing time on target and degrading accuracy. From Recklin's testing emerged a tactical prescription offering the best chance of success: frontal attacks from 12 o'clock high. That approach minimized exposure to defensive fire by targeting the bomber's weakest arc, where fewer guns could be brought to bear. Early B-17 variants, including the F-model Wolfhound, carried only 2 or 3 flexible nose guns operated by the bombardier and navigator crew members who also had primary responsibilities for bombing and navigation and were not dedicated gunners. Those flexible guns mounted in the plexiglass nose had limited traverse and required the crew to move the weapons physically between positions. The glazed nose gave the bombardier an excellent view for aiming through the Norden bomb site but offered little protection for the men stationed there, and provided only modest frontal defensive fire. A bold, skilled German pilot could therefore attack from 12 o'clock high, diving slightly from above and ahead, fire a concentrated burst into the cockpit and forward fuselage to disable the pilots, and then break away before the bomber's defensive guns could track effectively. That frontal attack doctrine had been pioneered by Headman Egan Meir of Jagdgeschwader II in late 1942, shortly before Wolfhound was captured. Meir's combat experience and analysis made clear that most of the B-17's defensive fire was concentrated to the rear and flanks, leaving the nose comparatively exposed. A head-on intercept created a combined closing speed exceeding 500 miles per hour, the fighter diving or running at roughly 350 to 400 miles per hour, while the bomber steamed toward it at about 150-180 mph. That closure translated to a relative approach rate of roughly 733 feet per second, giving the bomber's forward gunner barely 2 seconds to acquire, track, and fire. As the attacker flashed through the sight line, those 2 seconds demanded astonishing accuracy and calm from the defender, tracking a fast-closing target, estimating lead, and squeezing off effective bursts despite wind blast, vibration, and the adrenaline of a fighter bearing down on you. For the attacker, the geometry was simpler. The target filled the gun sight and required less lead than a crossing shot. When executed with nerve and skill, the frontal pass was devastating. Some German pilots who mastered it shot down multiple fortresses in a single sortie. The maneuver, however, imposed extreme psychological and physical strain, closing into a 4-engine bomber until it filled the windscreen, and waiting to fire at point-blank ranges of 200 yards or less, tested a pilot's discipline. Any premature pull-up wasted precious ammunition and ruined the attack. Many pilots broke off too soon, frightened by tracer streams and the roar of the nose guns, or were caught by the top turret as they passed. Even successful head-on strikes could be fatal to the attacker. The enormous closing speeds left almost no margin for error, and a delayed breakaway sometimes produced catastrophic mid-air collisions that killed both crews. The B-17's rugged forward structure also reduced the payoff of frontal hits, unless cannon fire struck the cockpit directly or knocked out multiple engines at once. Many fortresses kept flying and fighting despite grievous nose damage. For German pilots, this meant that kill often required total destruction rather than mere impairment, because a crippled fortress that limped home represented a failed interception and another airframe America could repair and return to service. Reconstructions from Recklin's tests combined with combat reports funneled to frontline units produced tactical bulletins, training films, and intelligence summaries spread throughout the Luftwaffe. Clear knowledge of the B-17's strengths, but little that could undo them at scale. Between May and early June 1943, Wolfhound underwent further trials in Department E3 under Otakuno's supervision, concentrating on engine and performance work. Engineers mapped power output across altitudes, gauged supercharger efficiency to find optimal operating points, charted fuel consumption and range under varying weights and flight profiles, and otherwise dissected the Pratt & Whitney Cyclone R1820 radial engines that propelled the fortress. Each power plant delivered around 1,200 horsepower at rated settings, and, with 4 installed, the bomber had roughly 4,800 horsepower available, enough to push the 30-ton aircraft toward near 300 miles per hour speeds at altitude and to support operations above 35,000 feet where conventional German fighters struggled without specialized equipment. German analysts concluded Boeing and its suppliers were turning these complex heavy bombers out at production rates 5 to 10 times greater than comparable German heavy bomber output figures that seemed impossible, until multiple intelligence streams confirmed them, and the implications for an industrially driven war were chilling to German planners. On June 12, 1943, Wolfhound featured in an exhibition at Lurz Airfield for Luftwaffe commanders and technical officers. Displayed alongside other captured Allied types, a consolidated B-2 for Liberator showcased a different American approach to long-range bombing. AP-47 Thunderbolt illustrated an emphasis on toughness and heavy armament in fighters. AP-51 Mustang hinted at the looming menace of long-range escorts. A twin-engine P-38 Lightning demonstrated unconventional U.S. design solutions. An Avro Lancaster and a de Havilland Mosquito represented British heavy and fast bomber concepts. And a Hawker, Typhoon, and various Spitfire marks highlighted British ground attack and fighter evolution. The exhibit served not just to teach recognition but to demonstrate captured technologies engineers might adapt and to drive home the scale and quality of Allied manufacturing. Even casual observers noted the contrast. American parts fit with precise tolerances. Surfaces were smoothly finished, and assemblies showed systematic, repeatable production methods rather than the ad hoc repairs and mismatched panels increasingly visible in German airframes hampered by bombing, disrupted supply, and forced labor. After the show, Wolfhound returned to Recklin for a final test series before being cleared for limited operational use. In July 1943, engineers fitted towing gear and evaluated the fortress as a glide for the DFS 230 program, checking towing procedures, release mechanisms, and formation handling between mid-June and early August. Technically, the B-17 proved capable of the task. It's for engines delivering the muscle required to tow loaded combat gliders to operational heights. Strategically, however, Germany lacked the transport fleet, fuel, and experienced airborne forces needed to exploit the capability after the heavy airborne losses in Crete and other costly operations. In September 1943, Wolfhound moved from the test establishment into active service with one of the Luftwaffe's most secretive formations, KG-200. Based at KG-200's portfolio included long-range reconnaissance using aircraft that could blend with enemy formations, clandestine insertion and extraction of agents, supply drops to isolated units or partisans, and trials of experimental systems too sensitive for conventional units. The unit operated an eclectic fleet of German types and captured Allied machines, chosen for mission fit rather than logistics simplicity. The B-17's long range of roughly 2,000 miles, its high-altitude capability above 25,000 feet, and its ability to sustain heavy damage made it attractive for such special tasks. Captured fortresses could slip into Allied-controlled airspace by masquerading as friendly bombers, buy precious time before interception, gather intelligence by observing formation conduct, or ferry agents and critical material across long distances. Wolfhound received night camo paint in blues and grays. KG-200 codes beginning with a 3 on the fuselage records suggest a 3 AE at one point, and operated in missions whose full details remain fragmentary due to lost archives and deep secrecy. Although historians later established that KG-200 employed at least 4 captured B-17s between late 1943 and mid-1944 for operations across Europe, the Mediterranean, the Middle East, and North Africa. Asterisk Hans Verlier continued to fly captured fortresses that cycled through Recklin. On October 9, 1943, B17F serial 4230336, nicknamed Miss Nonley to by her crew, crash-landed intact in a field at Nurholm Estate in Denmark after engine trouble on a mission over Germany. The crew bailed out and recovery teams moved quickly, and Lear himself flew the type from the field to Esbjerg and on to Recklin for evaluation. But he could handle and ferry an unfamiliar American heavy bomber from a farm field with no manual or checkout procedure underscored both his exceptional test pilot skill and the forgiving handling that made the B-17 resilient in emergencies. Miss Nonley too received German coding and served in tests at least through December 1944. Each newly captured fortress provided fresh material for engineers and tacticians to study. Even as the strategic tide the tests revealed continued to worry German planners, engineers examined successive production blocks to spot design changes that might reveal weaknesses to exploit or improvements that demanded new German countermeasures. They fired different ammunition types at B-17 structure to determine the best attack profiles for fighter pilots, testing how German cannon rounds fared against American armor and self-sealing tanks. 20mm shells proved only marginally effective, while 30mm hits were catastrophic when they connected. What emerged from these painstaking trials was a clear picture. By 1943, the B-17 embodied the apex of American bomber design and a defensive firepower that fundamentally changed the calculus of daylight strategic bombing. Recklin's test pilots crunched the numbers. A single B-17G, the most heavily armed variant entering service in mid-1943, carried 13 Browning M2.50 caliber machine guns arranged to give near-complete defensive coverage. Each gun fired standard .50 BMG rounds at roughly 750 to 800 rounds per minute and could sustain bursts for minutes, limited only by ammunition, supply, and barrel heating. A full B-17G typically carried about 7,500 rounds, distributed among positions so that each station had hundreds of rounds available for long European missions. The tail turret held about 500 rounds per gun, 1,000 rounds total. The top turret, similar quantities. The cramped ball turret, 250 to 500 rounds per gun, depending on mission and gunner size. Waist guns, 600 to 800 rounds apiece. And nose positions, including the GMO Dulcin turret, carried comparable loads. When Recklin calculated all guns firing together, the result was staggering. 13 guns at approximately 750 revolutions per minute produced an aggregate rate approaching 10,000 rounds per minute, roughly 160 heavy rounds, entering the surrounding airspace every second and filling an approach corridor with lethal projectiles. Asterisk, American doctrine never sent fortresses alone. Daylight strategic bombing relied on mutually supporting masked formations developed and refined through bitter experience in 1942-43. The combat box placed bombers in tight, three-dimensional arrays, so each aircraft's guns covered its neighbors. 3 aircraft made a squadron element, squadron elements stacked formed, squadron boxes of 9, and 3 squadron boxers comprised a group box of 27. Some groups operated with 4 squadrons, 436. Even conservative mixes of F and G models meant a group could field well over 180 heavy machine guns. 3 such groups in a wing produced 54 to 81 bombers and some 500-700 machine guns, creating lethal interlocking fields. German attackers described approaching these formations as flying into a wall of tracers, a vivid image that conveyed both the visual spectacle and psychological shock of mass defensive fire. At typical engagement ranges of 400 to 800 yards, every bomber gunner who detected an attacker opened up simultaneously, and 50 or more heavy guns might concentrate on a single fighter, making head-on passes terrifying and often ineffective unless executed perfectly. Asterisk, Luftwaffe after-action analyses showed the arithmetic favored the defenders. Rear attacks required, on average, about 20 hits from 20mm cannon shells to destroy a B-17, a figure that assumed hits struck a range of vulnerable systems rather than being concentrated, with pilot accuracy against evasive targets around 2% derived from gun camera and ammo expenditure analysis. Achieving those 20 hits from behind might demand roughly 1,000 20mm rounds. Early FW-190s carried roughly 500 rounds of 20mm between 2 guns. Even later Forcanon builds only managed 500 to 600 rounds total, seldom enough for more than 1 or 2 sustained runs. Meanwhile, the fortresses kept firing their thousands of .50 rounds throughout missions. And while individual gunners' hit rates were low, sheer volume made hits statistically inevitable when many bombers engaged one attacker. Luftwaffe fighter losses rose steadily through 1943 as bomber streams swelled. Escort fighter coverage improved, and German training and replacement rates failed to keep pace with attrition. Asterisk, frontal attacks did produce better kill ratios for highly skilled pilots. But the tactic demanded extraordinary nerve and precision. A head-on pass created closure rates over 500 miles per hour, compressing the optimal firing window to perhaps 2 seconds from roughly 400 to 100 yards. The attacker watched the bomber swell in the windscreen to a massive target and had to hold course. Wait until point-blank range, around 200 yards or less. Fire a concentrated burst, and then break away at the right instant. Hesitation or early pull-off wasted precious ammunition. Delay risked collision. Some pilots who pressed too hard collided with their quarry, and both crews were lost. Even lethal frontal strikes often left a fortress flying unless the cockpit was hit or multiple engines were simultaneously disabled, meaning the attacker had to achieve near-total destruction to prevent the bomber returning to base and being repaired. Recklin's practical access to intact fortresses transformed German tactical training. Pilots and ground crews walked around and through captured B-17s, examined gun positions and fields of fire, sat in the waist and ball turrets to learn traverse and elevation limits, and mapped blind spots. They flew realistic attack runs in training, filmed passes from chase planes, and produced instructionals reproducing likely engagement angles, closure rates, and exposure times for frontline units. That methodical study allowed experienced pilots to exploit specific vulnerabilities. But by late 1943, the Luftwaffe was losing veteran airmen faster than replacements could be trained. Raw new pilots lacked the hours and composure to carry out complex, high-risk maneuvers under fire. American designers and crews didn't stand still. Combat experience and crew feedback drove incremental improvements. And the B-17G's introduction in late summer-fall 1943 added a chin turret under the nose, a remotely operated mount controlled by the bombardier through a computing site that markedly strengthened frontal defense. The chin turret, together with cheek guns, nose positions, and a top turret that could swing forward, allowed a G model to bring 6 to 8.50 guns to bear on a frontal attacker, turning the once favored head-on pass into a far more dangerous maneuver. In response, Luftwaffe tactics shifted again. Some units attacked from steep high angles to exploit elevation limits. Others tried approaches from below the nose to slip under chin depressions. And some adopted standoff methods using unguided rockets, launched from under wing tubes to break up formations by blast rather than direct hits. Rockets, like the Werfer Granite 21 centimeters, promised formation disruption through blast and fragmentation. But they suffered poor ballistics, limited accuracy beyond approximately 800 yards, heavy drag that degraded fighter performance, and left the launching fighter vulnerable to escorts. By 1944, long-range American escorts such as the P-51 and P-47 long-range variants increasingly accompanied bomber streams to and from targets, denying German fighters the relative sanctuary they once enjoyed in exposing rocket-carrying interceptors to lethal counterattack. Technological escalation continued. The Luftwaffe introduced 30mm Mk-108 cannons, capable of destroying bombers with few hits, and experimented with larger rockets and other unconventional tactics. While the Americans refined formation technique, armor, and escorts yet none of these tactical or technical adaptations erased a fundamental strategic reality. American industry could replace losses faster than German industry could destroy them. Every fortress shot down represented a tactical success for the pilot who scored the victory, but rarely a strategic dent in the Allied campaign because production lines in Seattle, Long Beach, and Burbank turned out replacements rapidly. Allied output figures underscored this imbalance. Manufacturers produced thousands of fortresses during the war years. Boeing's Seattle plant alone built thousands. Douglas and Vega contributed significant numbers, and peak monthly output in 1944 reached production rates that astonished German intelligence, which repeatedly corroborated the numbers. German four-engine bomber production never matched these figures. The Heinkel He-177 suffered chronic development and reliability problems. In total, German heavy four-engine output remained a fraction of American totals. Recklin's engineers learned why the Americans achieved such volume. Modular construction, standardized parts, and assembly methods optimized for mass production rather than artisanal perfection. Subassemblies built in different factories fit together with minimal hand-fitting. Standardized fasteners reduced inventory complexity. Straight panels and limited compound curves eased forming operations. In simplified assembly sequences, let semi-skilled workers, many women newly integrated into wartime industry, build complex airframes quickly using jigs and fixtures. German reports mixed admiration with frustration. The methods explained how Boeing could complete fortresses at astonishing rates. A manufacturing philosophy prioritizing interchangeability and throughput over bespoke craftsmanship that German industry, hamstrung by strategic choices, resource limits, bombing, and decentralized production, could not easily replicate. German factories still relied on traditional construction techniques with hand-fitted components, riveted assemblies, and skilled craftsmen performing most operations. So building a single heavy bomber took weeks. The strategic implications were unavoidable to anyone who understood mass production. Even if German fighters maintained favorable kill ratios, shooting down 2 or 3 bombers for each fighter lost meant little win. American industry could sustain such losses indefinitely, and German industry could not. By mid-1944, that reality was obvious even to the most hopeful commanders. The question was no longer who would win the air war, but how long Germany could continue fighting against an overwhelming material disadvantage before collapse. Wolfhound and the other captured B-17s at Recklin taught the Luftwaffe everything it needed to know about the fortress as a weapon system. They documented its strengths, rugged construction, and heavy defensive armament, and its weaknesses, vulnerable early model noses and specific blind spots in gun coverage. Engineers recorded range, altitude, bomb load, formation behavior, and limitations such as the dependence on formation, integrity, and susceptibility to determined frontal strikes. They devised tactics which, when executed by calm, highly skilled pilots, could destroy B-17s despite their defensive firepower. But no tactical insight could overturn the arithmetic of industrial capacity. For every German pilot who mastered attacks on fortresses through Recklin training or combat, the Americans trained 10 new bomber crews. For every fortress shot down, American factories built several more. Disrupting a raid did not end the campaign. Dozens more sorties would fly the following week with larger formations. The defensive firepower that impressed German evaluators was only one element of a broader system designed to project American strategic bombing deep into enemy territory despite stiff opposition. The B-17 combined more than 2,000 miles of range, high-altitude performance above 25,000 feet, bomb loads from roughly 4,000 to 8,000 pounds depending on the mission, a structure that absorbed heavy damage, and interlocking defensive weapons into a package that, multiplied across hundreds of mutually supporting aircraft, changed the nature of warfare. Luftwaffe General Adolf Galland, one of Germany's top aces and later commander of fighter forces, wrote after the war about the difficulty of countering American daylight bombing. He admitted individual German pilots often had superior training and far more combat hours than many American bomber crews, who were frequently on their first tour, and that German fighters, particularly late-war types like the Focke-Wulf FW190D9 and the Messerschmitt BF-17 could outperform B-17s in speed, climb, and maneuverability, while their cannon delivered explosive hits far deadlier than .50 caliber bullets. Yet despite these advantages, German pilots could not stop the daylight offensive that systematically destroyed industrial capacity, and Galland placed American industrial output at the center of that failure. The captured B-17s made this fact indisputable for engineers and planners. German technicians disassembled every system, examined every detail, and evaluated design choices with thoroughness that left little to criticize. The fortress represented mature engineering executed with high-quality manufacturing and integrated technologies that formed a coherent weapons system. No amount of tactical ingenuity or individual bravery could bridge the material gap in a war of attrition. Hans Vera Lehr flew scores of captured types at Recklin and other evaluation fields, over 125 aircraft models in total without a single major accident. And his post-war writings combined professional respect for Allied aviation with frustration at German industry's inability to match Allied production and organizational efficiency. He flew B-17s, B-24 Liberators, Avro Lancasters, Soviet Peta South, and many fighters. Each machine revealed specific lessons about national design philosophies. But the B-17 remained the most strategically consequential because it embodied American strategic bombing doctrine in metal and systems. Every aspect of the fortress supported missions to penetrate deep, deliver heavy loads with precision, using the Norden bombsight and return, despite enemy fighters and flak. The defensive armament that so impressed German evaluators was the linchpin enabling those missions. Without the machine guns and the interlocking formations they allowed, daylight strategic bombing would likely have been abandoned in favor of night operations that sacrificed accuracy and effectiveness. The B-17's guns did not make it invulnerable. Thousands were shot down by fighters and anti-aircraft fire, but they made enough aircraft survivable to complete missions and to replenish crews who would train replacements. Over 2 years of sustained operations, the cumulative effect of hundreds of missions systematically crippled German industrial output, oil production, transportation, and military manufacturing. By the time Wolfhound was destroyed in an American raid on Erlenberg Airfield on April 10, 1945, strategic bombing had largely achieved its aims. German industry lay devastated in the Ruhr and other industrial regions. Fuel shortages grounded much of the Luftwaffe despite remaining airframes, and transport breakdowns prevented critical supplies from reaching frontline armies. The captured fortress that had taught the Luftwaffe so much about American defensive power had become a symbol of the futility of opposing overwhelming industrial strength. German pilots who learned attack techniques from flying captured B-17s found their skills increasingly irrelevant as American bomber streams swelled to thousands of aircraft escorted by long-range fighters. Individual excellence and tactical mastery could not offset catastrophic numerical and material inferiority. The history of captured B-17s in German service is an odd coda to the broader story of the strategic bombing campaign. American-made aircraft, flown by American crews, forced down or shot down by Germans, then repaired and flown by German pilots, provided unique insight into Allied methods and capabilities. They revealed weaknesses that skilled Luftwaffe pilots could exploit and trained recognition and attack procedures that saved lives. They supported clandestine operations and served in a variety of tactical roles in 1943-44. Yet they also exposed Germany's impossible strategic position by laying bare the scale of American industrial output. Every hour German mechanics spent refurbishing a captured fortress diverted expert labor from German maintenance needs. Every gallon of fuel burned in evaluation flights was fuel not available for combat. Every round fired in test runs represented ammunition Germany could ill afford. Meanwhile, American factories produced fresh fortresses daily. The production figures remain striking decades later. Boeing's Seattle plant built thousands of B-17s across variants. Douglas's Long Beach facilities added several thousand, and Vega in Burbank contributed large numbers, summing to over 12,700 by war's end, with the last delivered in May 1945. Each bomber contained roughly 40,000 parts, sourced from hundreds of subcontractors. 4 R-1820 Cyclone engines, producing some 1,200 horsepower apiece. Miles of wiring, thousands of pounds of formed aluminum, and up to 13 heavy machine guns with thousands of rounds. Germany never produced even 2,000 4-engine heavy bombers during the war. Despite starting with an advanced aviation sector in the 1930s, and the reasons went far beyond factory space. American doctrine prioritized heavy strategic bombers for deep penetration strikes, while Germany emphasized medium and dive bombers for close air support. A fundamental difference in military philosophy. Geography and security also mattered. American factories, shielded by oceans, expanded without facing invasion, while German industry worked under constant Allied bombing that destroyed facilities, killed workers, and disrupted supply chains. The U.S. educated and produced thousands of engineers, managers, and technicians annually, while Germany faced manpower shortages as casualties mounted. Most fundamentally, American political and economic systems proved more adaptable to total war mobilization than the rigid Nazi hierarchy with competing power centers, poor decision-making, and ideological constraints. All these factors combined to produce the industrial advantage that decided strategic outcomes. When Luftwaffe officers examined Wolfhound at Recklin, tested systems, and flew evaluation sorties, they were studying American industrial civilization and its capacity to sustain prolonged production. The lesson should have been obvious to anyone objectively analyzing American manufacturing. You cannot defeat an enemy who builds bombers faster than you can shoot them down, who trains crews faster than you can kill them, and who delivers greater bomb tonnage than your whole industrial base can match. The defensive firepower that impressed German test pilots was only the visible tip of a larger system of economic and organizational strength. The true strategic weapon was not the 13 machine guns on a B-17G, but the American economic and industrial machine that designed, produced, and fielded 12,731 fortresses, while simultaneously manufacturing hundreds of thousands of other weapons, vehicles, and munitions needed for global war. Tactical brilliance, pilot skill, and courage could not overcome such an overwhelming imbalance in production. Hans Vera Lehr, after flying dozens of captured Allied types and seeing firsthand the scale and quality of enemy equipment, concluded that Germany had effectively lost the war. By 1943, based on industrial mathematics, the numbers predicted defeat with grim certainty, leaving only the timing and human cost as open questions. The captured B-17s answered many tactical questions for German pilots. They exposed blind spots, identified vulnerable systems such as hydraulics and oxygen supplies, and revealed attack profiles that offered the best chances of success, but they could not solve the fundamental strategic dilemma. Asterisk, how do you stop 10,000 bombers when you can scarcely produce 1,000 fighters a year? How do you protect cities from endless raids when your pilots fly multiple missions until they are killed, wounded, or exhausted? How do you sustain industrial output and public morale when workers know American bombs will eventually find their factories? Nazi Germany's strategic errors in the 1930s, assuming quick victory before enemies fully mobilized, meant that once the war turned into a contest of industrial endurance, Germany's fate was sealed. The B-17, with its ability to throw massive defensive fire, absorb horrific damage, and keep flying, embodied American industrial and organizational superiority and delivered a strategic verdict on the war's outcome. Bombers came in ever-increasing numbers. Escorts grew stronger, targets burned, and there was little the Luftwaffe could do to stop the campaign despite heroic efforts. Recklin's pilots left with reluctant admiration for American engineering, manufacture, and organization. They respected the fortress's toughness, its crew-focused design, and its devastating defensive firepower. But that respect did not alter the outcome. By late 1944, many captured B-17s had been destroyed or rendered unflyable by Allied attacks on German airfields, by maintenance failures caused by broken supply chains, or had been used on special KG-200 missions until the war's final weeks. Their intelligence value had largely been exhausted. The Luftwaffe had learned nearly everything worth knowing about the fortress, its blind spots, system vulnerabilities, and effective attack techniques. Yet that hard-won knowledge became increasingly worthless against 1,000 bomber raids escorted by hundreds of fighters that overwhelmed defenses by sheer numbers. Individual German pilots still achieved remarkable successes against B-17 formations, and some aces used techniques learned from examining captured examples at Recklin. But such heroics could not undo structural industrial inferiority. For every ace who survived long enough to perfect his craft, 10 inexperienced pilots died early, and by 1944, the average life expectancy for a German dayfighter pilot was measured in weeks rather than months. The Americans, by contrast, rotated crews home after completing tours, initially 25 missions. Later, 35 so survivors returned to training units and passed hard-earned lessons onto new crews, preserving institutional knowledge bought with blood. Germany could not afford such rotation. Every experienced pilot stayed in combat until killed, captured, or incapacitated, eroding unit experience levels. Captured B-17s taught the Luftwaffe much about American defensive power through methodical study, and the experience of fighting 1,000 bomber raids taught harsher lessons about Allied resolve, resources, and industrial endurance. The ultimate lesson arrived in May 1945 when the guns fell silent and Germany lay shattered between Soviet pressure in the east and Western Allied advances in the west. The bombers had done their work over years of sustained operations, and the defensive firepower that so impressed German examiners could not prevent the